Today, I will talk to you, especially focusing on the mechanism of neutron generation. So many cold fusion studies have been continued for more than 23 years. I think the information of the neutron is more important in order to find out the mechanism than others such as heat and energy generation. However, there are not so many reports according to the neutron. I can say that the neutron evolution is clearly came from the nuclear reaction. I think that the other reaction products, such as the heat and element generating from the transmutation reaction, can be said that the information quality is not so worse compared to the neutron. I have said the method of neutron generation. Until now, I announced 23 years before the first method, which is simple electrolysis of heavy water of the palladium. The next was 10 years before the method of deuterium gas absorption into a palladium rod at low temperature under intense magnetic field. And the other method was deuterium gas was absorbed into the palladium rod, and then cold hydrogen gas was injected into the rod. After that, the neutron emission was observed during not long duration. After I obtained many experimental results, I have understood that the deuterium was required for the occurrence of the neutron emission. When you use the hydrogen gas for the cold fusion experiment, you may have a slight neutron if you are lucky. In the test by the hydrogen, there are no way for the observation of neutron. It is so difficult. Deuterium is needed to generate the neutron. That means the reaction was occurred by day fusion. Neutron generation was also caused by the deuterium in other report. The technique how to generate the neutron has been many reported. It was found that there is a common factors, but there was a variety of ways to generate the neutron, and it can be understood by analyzing in detail. I have studied how to generate neutron easily. In this presentation, I am going to talk about the mechanism behind the reaction of these CA&R in order to stably control the generation of excess heat energy and other reactant. I want to talk about the introduction of new scientific methodology. I am going to show you along this flow. The first, I will talk a story using deuterium gas and the experimental procedure. Second, I want to talk some new result. These were achieved by varying the part of the experimental conditions. Third, I want to talk about the new results that have showed neutron generation. I think if I have time, I want to talk a theoretical explanation. This table shows the method using the series of CF experiments. It shows a summary of the paper that has published. It shows the CF reaction material, media, trigger, and products. These generated products were neutron, tritium, and heat. Most frequently used metal is palladium. Many of the researchers use the heavy water. In many reports, excess heat and energy has been detected in both light and heavy water. There are many reports on the neutron emission. I think that the neutron is considered to be among most important evidence showing that are caused from nuclear reaction. Almost of them do not indicate the correspondence between the theoretical coincidence of the relationship between the number of neutrons and the quantity of the heat. It is difficult to describe in the conventional theory. In any case, the energy of neutrons was near 2.45 million electron volt. This is the value of the energy caused by day reaction. In the first, the generation of the neutron has been described based on the theory of the normal thermonuclear fusion. In this case, the reaction was considered as dB fusion. And the case, the Newton energy is 2.45 million volt. And this picture shows the palladium electrode before left-hand side and after the electrolysis. Electrolysis was performed for more than several days or weeks. Typically, current density was 20 milliampere per square centimeter. Here, I want to focus on the metal surface after the electrolysis. We can find many metal particles that are less than 100 nanometer. These sizes are something less than 10 nanometers. This photo is an examination of the electrode before and after the test of platinum electrode. Platinum was electrolyzed for several days, 20 milliampere, same current density. You can see below size of 100 nanometer or metal particle for the surface of the platinum metal. This is a gold electrode. You can see also metal particle of the size 100 nanometer or less. Here, I will show you how to generate a neutron radiation. In this experiment, we used iron sodium oxide as a reaction medium. Reactant is at high temperature steam, vapor. Vapor is decomposed at the surface of the oxide into hydrogen and oxygen molecules. We have observed the occurrence of weak neutron emission during the test. This shows a conception drawing of the experimental condition. High temperature vapor go on the reactive metal surface. Vapor is decomposed into hydrogen and oxygen gas. At the time, radiation can be observed. This shows a schematic drawing of experimental setup. Reactor is the center bottom of this figure. You can see the measurement system and control system on the left-hand side, and the gas supplying system is right-hand. The reactor is drawn bottom of the figure. This photo is shown experiment setup. Reactor is seen center of the photo, and the reactor is covered metal and glass fiber insulator. You can see controlling and gas supplying system. This drawing shows a cross-section of the reactor. Reactor is divided into three parts. Containers, cathode material, and anode electrode. Cathode electrode is composed by small particle of alkali metal oxide. This is an outer and cross-section view of the typical reactor. The reactor has inner and outer pipes, and it has gas inlet and outlet. This graph shows a typical result of hydrogen generation. You can see the time change of vapor pressure and rate of hydrogen generation and temperature. This scale is pressure. Pressure go up something like 0.6 atmosphere, and immediately the hydrogen gas release. And the rate of the hydrogen gas release is something like 6 or 8 liter per minute. During the experiment, the temperature go up something like that. It takes 3 hours more. This graph shows the behavior of neutron generation. Neutron generation drawn up by red bottom line, red dotted line, this line. This is the neutron scale. Neutron generation, it shows the same change with the rate of hydrogen generation. Hydrogen generation and the neutron evolution seems a very similar coincidence with targets. This graph shows another result of hydrogen generation. You can see the time change for vapor, pressure, and rate of hydrogen generation and the temperature change. The same before. This shows the behavior of neutron generation. neutron generation also indicated by the dotted line. It shows the same change with the rate of hydrogen generation. This is the background level and little bit increasing. And this neutron generation rate is almost coincident with this hydrogen generation. It shows the temperature change measured at various positions on the reactor chamber. All positions at the reactor temperature rose up several 10 degrees with the test duration. Here, we can estimate the excess heat generation as 40 watt when the temperature rises up of 130 degrees centigrade. And this shows another example for neutron and hydrogen generation. Neutron generation, this dotted line, neutron generation indicated by dotted line is changing with the rate of hydrogen generation. Neutron generation shows a high value at the beginning, only at the high, in the beginning, and then it decreases with the time and fall into the background level. This shows the mass spectrum of the generated gas. This is mistakes. 66% is hydrogen and other 35% is oxygen. Completely the water was decomposed. We confirm weak neutron emission by the reaction of water decomposition on a reactive material. The reaction rate related with the amount of the water decomposition. If we can assume that the reaction was occurred by two deuterium atoms, the reaction probability can be estimated as from 10 to the minus 16th to 10 to the minus 10th per daily pairs per second. I show another method to generate neutron. We have used the material particle, metal particle as reactive materials. In this experiment, nickel was used. Reactant was the deuterium gas. Reaction gas was injected into the reactive metal surface. Then we have confirmed the occurrence of a strong neutron emission. This slide shows conception for experiment condition. H2 or J2 gas injected into the reactive material surface, and this gas was absorbed and released. After that, we have observed the neutron emission. This drawing shows the experimental setup. Reactor is the lower right corner of this graph. There are vacuum pumping system and gas supplying system, and the radiation maintenance system is there. This shows the cross-section view of the reactor. Reactor was divided into three parts: containers, cathode, and anode. These electrodes were used for the activation process of the material. Cathode electrode is composed by nickel metal particle. This photo shows the reactor window, and the electrode during the activation process by plasma discharge. Upper graph shows the time change of reactor temperature and gas pressure. This is gas pressure. This is gas pressure. This actually is the temperature. You can see that the temperature was almost stable, but gas pressure was changing, although it have been kept constant. You can see the bottom graph. This very strong neutron generation and gamma emission was occurred. This is the gamma emission, and this is the neutron. I put this force. This is a 10 millisievert per hour. This shows a test of palladium particle that was supplied to the gas, the same condition. Temperature was shown as at a glance stable because it was measured on the surface of the reactor. In this case, the measuring response was so slow. The gas pressure was changed by absorption with the palladium, although it has been kept at a constant pressure. We can see very strong neutron generation and gamma emission here. This shows the case of palladium particle that has been supplied Day2 gas. Temperature was measured at the surface of the palladium electrode. Here. It shows rapid temperature rise by the absorption of deuterium. It reached 1950 degrees centigrade. At this case, temperature was directly measured on the test material surface by a pyrometer. Then the measurement response was very fast. This is even if the gas pressure had been kept at a constant, the change was so large because palladium particles have absorbed and released the deuterium gas according with the Newton. Here you can see the intense generation of neutron and gamma radiation. This shows the case of palladium particle that was supplied normal hydrogen. The gas pressure was stable and the temperature was also no changes in the upper graph. Here we can see no neutron generation and gamma emission observed in bottom graph. These factors stayed at the background level. We can understand that no reaction occurred if you use the light hydrogen. When hydrogen gas was absorbed into the reactive substance, we can confirm the intense neutron radiation. The neutron emission rate was released with the amount of the gas absorption. If we assume that the reaction have been induced with the reaction of the two deuterium atoms, we can estimate that the reaction probability is 10 to the minus 10th per daily pair per second. So next is my speculation of the theoretical aspect. I have time? Enough time? Okay, 5 minutes. Okay. We assume in order to consider the mechanism to generate the neutron radiation, reaction takes place inside the reactive particle of material with the hydrogen atoms. Dynamic interaction of electron and hydrogen atom in the particle are quite different from the bulk. We use the method to approximate LCMO for the orbital calculation of electron and hydrogen atom. Mass of electron in the metal particle was found to exhibit a large value by the calculation. These slides show the methods that were used in the theoretical analysis. We focus on the behavior of the electron in the metal particle. Several reports have pointed out that the dynamic behavior of the electron is very different in the metal particles from the behavior in normal bulk. Electron is confined to a narrow band, especially in the nanoparticles. This means that the electron conduction bandwidth is very limited. Such electron will be affected by the other potential of atom and electron metal particles. For the band calculation of the electron in the nanoparticle, we use the approximation method of the LCMO in the case of irregular atom arrangement. Hydrogen concentration palladium was used as 0.76. Titanium was used a value of 1.67. We use the hydrogen concentration as a value of unity in nickel, platinum, and gold. And this is a perovskite structure for the alkali metal oxides. In recent years, I found that the behavior of conduction electron is different from the normal metal in the case of experimental methods. We still do not have calculated the internal behavior of electron and this structure. And this shows the electron mass of E hydride showed a large value in the hydride of palladium and titanium. The value is increased with the decreasing of the metal particle size. The effect is small for the platinum and gold metal particle. Then, when the atomic nucleus of hydrogen exists in the nanoparticle, the atom has the possibility that an atomic diameter in the appearance becomes small to take the E hydride as the electron orbit of nucleus. As a result, E hydride reduces the nucleus Coulomb barrier of hydrogen as shown in figure. As a result, the nuclear fusion reactions are easily occurred by a tunnel effect. Left graph shows the neutron generation by daily reaction in the hydride. Right graph shows the daily cross-section represented by Gamow relationship. We can estimate the relation and probability of our test. This figure shows the nuclear reaction probability for the hydrogen as a function of the temperature. The probability is increasing above 10 to the 9th Kelvin. The reaction probability reaches 1 unity at reaches 10 to the 10th Kelvin. The calculation of the tunneling probability for the change of the Coulomb potential or the proton is shown in this figure. As for reaction probability by the tunnel effect, if the barrier potential decreases by only 50%, the probability increases by 10 digits. I had the talk of the occurrence of the neutron. Confirmation of the neutron is one of the most important works in the CF research, as saying many times. I, for many years, have been experimenting on fusion. The center of the experiment was set in particular confirmation of the occurrence of the neutron. I tried many varieties of the experimental method in this study. In most of the cases, I have not obtained the expected result. However, in recent years, I have reviewed the experimental of the past, and then I have found some new result. It was the fine particle that have generated on the various metal samples after the experiment. And recently, the result of experiment using the fine particle of nickel have been more attention. But the report of heat, even if it has particularly large, it is no variable information. We have to confirm the clear product by the reaction. This time, we were able to generate a neutron using metal particle and hydrogen gas. Theoretical researchers have also published heavy fermion theories. Although this electron is theoretical, if you use the wave function as a dynamic of time encoding so that behavior is really heavy, we can describe very well the experimental result by using these theories. This theory and the nanoparticle can be expected to become a powerful weapon of the Newton CF phenomenon. My presentation is almost over. Thank you for your attention.
Questions? Yeah, let's go one by one.
Thank you. I consider this to be an extremely important paper. This is the second time this morning that the probability of growth of new elements within the Earth's structure is available by means that are natural. The question I have is that, do you think this process also could account for the sonnefusion neutron and gamma results?
Yeah, exactly. So I especially focused on neutron gas because I wanted to measure the neutron, but I also make sure the transmutation material using a light water, and also also on heavy water, both of them.
Thank you.
Please.
Just a comment. I think the helium-3 detector using only one is very noise sensitive. So you have to check by using more than two systems, cross-checking if these are really neutron or not. And also you say this is neutron at 2.45 neutron from the reaction, but you have no proof of that. It might be something else if it were neutron even. So you can say that kind of conclusion from the results. So be careful to say the conclusion.
Thank you very much for your suggestion.
Okay, next, please.
Have you variation of concentration deuterium in hydrogen? And what you think about this concentration? Oh, I don't find this results. Yes, you don't do. Yeah. You do. And why? You didn't think that it is dependence of optimum in this concentration.
Excuse me. Dependence of what?
Maybe there are some experiments when Ramadanov, such as which indicates that there is optimum concentration of deuterium in hydrogen when the result is best. You didn't do?
No, I didn't.
Yes.
Okay, more questions? Let me add one. Among your detections, actually spectroscopic will be much better. For example, gammas, if you use a high frequency germanium detector, even worse one, if it's not available, sodium ion detector will tell you the energy spectrum, which you can make some more better measurement. For neutrons, you use a helium-3, but that's for a dosimetry. So if you use the say a plus scintillator, for example, detection efficiency is much higher, and using this endpoint, you could roughly know this neutron spectrum if there is.
I agree. Thanks.
Yes, fine.
From your graphs, I was not sure whether you are measuring the neutrons in the form of pulses or in the form of a current.
What is a current?
No, if you are using a neutron chamber, an ionization chamber, and measuring the current, I wasn't sure from the plot. But if it is in the form of pulses, and since there has been suggestions that it could be due to electromagnetic pickup and so on, my suggestion is from our experience, a very simple way to find out if these are neutrons is to carry out a probability distribution. If you have a Poisson distribution for the neutron pulses, then chances are it's a new real nuclear process.
Oh, I see.
But if it is erratic, the neutrons, then these are pickups due to, as he said, using BF3 counters, helium-3 counters, that problem is always there. Thank you.
Thank you.
Okay, more questions? If not, let's thanks the speaker again.